Okay, so I'm now sharing my slide. I hope everyone can see my slides now. Um, I hope everyone can also hear me well. Okay, let's see. Okay, thank you. Okay, so I guess I can now start. Okay, so I think last time we discussed about grain size analysis, okay, the grain size distribution curve. And then we also discussed the unit weight volume relationships. Okay. So I think this time we'll try to discuss about plasticity and soil structure. Okay. Um, I think one of you asked the question last time. What are the usual tests that we prescribe in a normal geotechnical investigation? Okay. So normally, what we prescribe is the grain size test. Okay, the grain size distribution curve. Okay, we require that the grain size data. We also would require the unit weights of the soil. Okay, and then the next items on the list will be this one now. No? This topic that we will be discussing, okay, which we basically call the Atterberg limits. Okay, so these are what we call the normal routine test that we specify, or at least I specify when I um, require a geotechnical investigation for a particular project. Okay, so let's try to have some idea of these Atterberg limits. I'm not sure in your laboratory if you're already doing this one. No? Okay. So when clay minerals, okay, so I think last time we discussed about clay minerals. No? I think for the clay minerals, if you try to recall, there are many clay minerals, but I think as far as my experience is concerned, the most common is the Eli clay, the kaolinite clay, and the Mont Morillonite clay minerals. Okay? These are the usual clay minerals that we can find in the field. Okay? So when these clay minerals are present in a fine grained soil, okay, there's because there's what you also call a coarse grained soil. I think for our next topic, we will be classifying now. No? We will now go into soil classifications with respect to coarse grain and fine grain. Okay. Now, for the moment, in the case of a fine grained material, okay, these are basically the fine sands, the sills, and the clays as well. No? Okay, these are the fine grained soils. Okay. So when clay minerals are present in a fine grained soil, okay, the soil can be remolded, okay, in the presence of some moisture without crumbling. Okay, so I guess you can still recall, no, when we were even I myself, when I was still young, I can still recall I was playing with this. We call this uh, this molding clays. I'm not sure if that's still the right term for that. And this, when we were still young, we like to play with these clays. No, we try to mold them. Okay, so basically that's a property of a clay material. No, you can mold them. Okay, especially in the presence of some moisture. Okay, without crumbling. Okay, that's a basic property of a fine grained soil material, especially clay. So this remolding process, this is basically due to the cohesive nature, no? Which is caused by the adsorbed water surrounding the clay particles. No? If you recall, last time we were discussing about adsorbed water within the clay particle. No? Okay. So because of that adsorbed water, then you have this cohesive nature of this, especially the clay soils. Okay. So in the early 1900s, a Swedish scientist named Atterberg developed a method to describe the consistency of fine grain soils with varying moisture contents. Okay. So at a very low moisture content, okay, or water content, okay, the soil behaves more like a solid. Okay. Now, when the moisture content is very high, the soil and the water may flow like a liquid, okay, which normally we don't like, no, as far as construction is concerned. Okay. So, depending on the moisture content, the behavior of a soil can be divided into four basic states. Okay. So, you have the solid state, the semi-solid state, the plastic state, and the liquid state. Let me just show a figure of that. So this is basically the four states. Okay, so we have the solid state, this one here, the semi-solid state, the plastic state, and the liquid state. Okay, so don't worry about these diagrams. These are all in the book. No, I just took them all from the book. Okay, so if you have the book, you can just refer to them. Okay. Now, so the moisture content, okay, in percent, okay, so the moisture content in percent at which the transition from a solid to a semi-solid state takes place is now defined as the shrinkage limit. No? Okay, so that's the moisture content. Now we are basically talking about moisture content. Okay, and then the moisture content at the point of transition from a semi-solid to a plastic state is now what you call the plastic limit. Okay? And then from the plastic to the liquid state, where the soil will now act like a liquid, is now what you call the liquid limit. Okay? So these parameters are now what you call the Atterberg limits. No? Okay. So if we go back to the figure, okay. So again, the transition between a solid state to a semi-solid state is now what you call the shrinkage limit. Okay. And then from a semi-solid state to a plastic state in your soil is now the plastic limit. Okay. Then from a plastic limit to a liquid limit is now what you call, or the transition is now the liquid limit. Okay. So the molding clays that we are playing, we're still young. Okay. Is somewhere around this plastic range. No? Okay. Okay. Where you can mold the clays. Now, with respect, no, to the stress strain diagram, no? Okay, yeah. So this is basically this x-axis is now your moisture content, no, in the increasing direction. Okay, so depending where you are, no? For example, if your soil is in the shrinkage limit state, okay, from the solid to the semi-solid state, okay, then if you try to test, okay, that soil material in the triaxial test, which we'll discuss later on, okay, then the stress strain diagram will look something like this, no? In such a way that for that soil material, you will need a higher stress. Okay, I hope you still recall your strength of materials. Okay, you need a higher stress for that soil to undergo a higher strain, something somewhere like this. So for your soil to have a strain like this, yes, for example, this one here, then it would need a stress something like this. Okay. Now, if your soil is between the semi-solid to the plastic state, no? Having a plastic limit um, value of the moisture content, then at the same strain, okay, if you look at this curve here, no? Having the same strain, okay, then you would only need a smaller amount of stress, okay? Smaller amount of stress to achieve the same strength uh, between this one and this one here. Okay? So that's the difference now between the soils having the shrinkage limit state, or between solid and semi-solid state, and for a soil between the semi-solid and the plastic state. Okay, so which means that this material here is softer compared to your soil material in this in these states. Okay, now if we are now on the plastic to the liquid state, okay, having the liquid limit moisture content. Okay, so it's now becoming like a liquid. Then basically you don't need any stress at all for the soil material to undergo the same strain. Okay, yeah, because it's now acting like a liquid. Okay, yeah. So these are now the behavior. No? Okay, that this is now the behavior of material between a solid to a semi-solid state. This one here, a semi-solid to a plastic state. This one here, and a plastic to a liquid state, basically having no stress, no, to undergo strain, because it's basically uh, more of the liquid state already. Okay. So that means that from the shrinkage limit to the plastic limit and to the liquid limit, you now have an increasing moisture content. Okay. So again, the shrinkage limit, the plastic limit, that's the PL, SL, and the liquid limit is now what we call the Atterberg limits, no? Because of the Swedish scientist Atterberg. Okay, it's named after him. Okay. Okay. So for a liquid limit device, okay, in the lab, I don't know if you have already done this, but if not, then you will be doing this in the lab. Okay, so you will have a liquid limit device. Okay, so a liquid limit device consists of a brass cup and a hard rubber base. Okay, so the brass cup can be dropped at the base by a cam operated by a crank. Okay. So to perform the liquid limit test, one must place a soil paste in the cup. Okay, and then a groove is then cut at the center of the soil path with the standard grooving tool. I will show a picture of that one in a while. Okay. So there are two types of grooving tools. You have the flat grooving tools and the wedge grooving tools. Okay. So by the use of the crank operated cam, the cup is lifted and then dropped from a height of 10 millimeters. Okay. Now with this process or with this procedure, the moisture content in percent, okay, required to close a distance of 12.5 millimeters along the bottom of the groove after 25 blows is now defined as the liquid limit, now as far as laboratory procedure is concerned. Okay. So this is now a picture of that one, of this liquid limit test. Okay. So this one here is now what you call your liquid limit device. Okay. This one here. Okay. Then this one here is a flat grooving tool. Okay. And this one here is a wedge grooving tool. No? Okay. Needed to slice no? The soil material. Okay. So this is now, okay, before the start of the procedure, you will try to slice the soil by the grooving tools. Okay, so the soil will now look like this. This is now the plan view. This is cross-section view. So the soil path will look like this before the start of test. Okay, then it will now look like this um, after the test procedure. Okay, so after how many blows, then the soil will try to close each other. Okay, yeah. Okay, so this is the, again the top. Sorry, this is my cursor. This is now the top view, and this is now the bottom view. No, okay, yeah. So just a picture of that. Okay, so again, this is now your liquid limit device. Okay, this is now a flat grooving tool. Okay, this is now a wedge grooving tool. Okay, and this is now the handle. Okay, so it will try when you turn this handle, then this cup will be raised up. And then as it goes down, then the soil will try to move. Okay, so here this is now the actual soil before the test. Okay, and then this is now um, the soil test, the soil sample after the test. No? Okay, and then you will try to measure 12.5 millimeters, no? For the groove closure. Okay, to define the liquid limit value. Anyway, you will be doing this in the lab as well. No? Okay. So the relationship between moisture content, okay, and the log of n, okay, where n is the number of blows, no? Because you will be again turning this handle, and then this cup will be raised up, and then will fall down, then raise up and fall down, and so on. So um, every time it drops, then that's the number of blows. Okay. So the relationship between the moisture content, okay, and the log of n is approximated by a straight line, okay, which you will basically plot in the lab. Okay. Now this line is now referred to as the flow curve. Okay. So the moisture content corresponding to an n value equal to 25 determined from the flow curve would now give us the liquid limit of the soil. Okay. So the slope of the flow line is defined as the flow index, okay, symbolized by I sub F. Okay, the flow index is now equal to this formula here. Okay, that's now the the difference in the moisture content. That's W sub 1, okay, minus W sub 2, okay, over the log of N sub 2 over N sub 1, where the n sub 1 number of blows corresponds to the moisture content, this one here, okay, and then the n sub 2 number of blows corresponds to the moisture content at W sub 2, okay. Okay, so just a note that these two water moisture contents are exchanged, okay, to yield a positive value, even though the slope of the flow line is negative. Okay? So thus, the equation of the flow line can be written in a general form as given here in equation 4.2. Okay, wherein the moisture content is equal to the negative of the flow index multiplied by the log of the n number of blows plus a certain constant. Okay, so just to have a sample of the flow curve. Okay, so this one here is an example of a flow curve, okay, for a liquid limit determination in the case of a clay silt. So for the moment, let's just have that. Next meeting, we will now go into the soil classification, okay, where clay silt is one of the soil classifications, okay. So that means here you do a certain number of tests. Okay, for example, here you have done actually 4 tests. Okay, with different end blows. Okay, with different end blows, and then you try to plot that. Okay, then draw a line which will now act as your flow curve between the number of blows in the log scale. That's your n, and the corresponding moisture contents. Okay. So once you now have this flow curve, okay, then you now try to look for the n value of 25, okay, as per definition of the liquid limit. Okay, so you try to project that up, then plot it here. That will now give you your liquid limit value, okay, which is now, in this case, that's 42%, 42% of moisture content. Okay, that's now your liquid limit. Okay, so if you go back to the graph, sorry, the chart. So here, the liquid limit value is about 42%. Okay, okay, okay. So now let's try to define a plastic limit. Okay, so the plastic limit is defined as the moisture content in percent, okay, in percent, at which the soil crumbles when rolled into threads of 3.2 millimeters in diameter. Okay? So this plastic limit is the lower limit of the plastic stage of the soil. Okay. So again, you will be doing this in the lab. No? So you will get a soil sample, then you try to play with it in the lab. Okay, try to roll it, okay, until it will now become threads of 3.2 millimeters in diameter. Okay, yeah, and then when it crumbles, okay, then that's now the plastic limit. Okay, so the plastic limit test is performed by a repeated rolling of an ellipsoidal sized soil mass by hand on a ground glass plate. Okay, and then this procedure for the plastic limit test is given by ASTM D4318. Okay. Now, again, when we prepare geotechnical reports, we state there in the geotechnical report the laboratory test that has been done for that particular project. And then we state there the ASTM standards that are being used for such test. So that whoever reads the geotechnical report would understand that, okay, they are doing a standard test, okay, which we can understand. Okay. So all laboratory tests in the geotechnical engineering practice, we follow, at least in the Philippines, we follow the ASTM standards. Okay. Um, and then we are very strict with that, especially if you're working in a company who is an ISO accredited company. Okay. That's ISO is the International Standards Organization. Okay. So you're ISO accredited. Okay. So after we have defined now plastic limit and the liquid limit. So the plasticity index, PI, is now defined as the difference between the liquid limit and the plastic limit of the soil. Okay. Or in formula, the PI, that's the plasticity index, is now equal to the liquid limit minus the plastic limit. Okay. So with that, we now have here some typical values for the liquid limit, the plastic limit, and okay, the activity of some clay minerals. Later on, I will discuss the formula for this. Okay, for the moment, let's just leave those values there. But for different clay minerals, no, such as the colinite, elite, and the montmorillonite clays, you have here the corresponding liquid limit values and the plastic limit values, at least the typical range, typical range. Okay. So you would see here that the liquid limit values are generally higher than the plastic limit uh, values. Okay. You can even have a liquid limit value as high as 900. No? Okay. For Montmorillonite clay, which is a bit problematic. No? When we try when we try to test clay soils, we always pray that we will not encounter Mount Morillonite clay minerals, no? Okay, because these are basically the clay minerals that would make the clay soil expansive, and an expansive soil. Okay. Now, as far as construction is concerned, we don't like expansive soils. Okay. Um, in the geotechnical report, when we prepare geotechnical report, we always state there the problematic soils. Okay, these are usually the collapsible soils, the expansive soils, or the swelling soils, and also the liquefiable soils, no? Due to earthquake. Okay, so in the geotechnical reports that I normally prepare, okay, I always specify this in the report. No? Okay, for your particular site, okay, we have found out there are some collapsible soils or some expansive soils, or there are some liquefiable soils. Okay, I just attended a meeting earlier this afternoon, wherein we were discussing a particular project wherein the site is a bit liquefiable, and we were trying to design for a power plant. Okay, somewhere here in Luzon. Okay, then based on my assessment, the site is liquefiable. Okay, so we are now discussing whether to do ground improvement works, such as stone columns, okay, or if we are to do board piles, okay, or deep foundations. Okay, so I hope this is now clear. For the activity, let's go back to that later on. Okay, now Burmester classify the plasticity index in a qualitative manner. Okay, as shown here. Okay, so if the PI value is 0, then we can say that the material is non-plastic. Okay, and usually I'm very happy if it is non-plastic. Okay, but if the PI is a 1 is to 5, that's slightly plastic. If 5 to 10, that's okay, you're having low plasticity there. It's plastic, but it's low plasticity. If 10 to 20, that's medium plasticity. 20 to 40 is high plasticity. And then greater than 40 is very high plasticity. Normally, we don't like this high plasticity soils, no? Because they create problems, no, in construction. Yeah. So the plasticity index is important in classifying a fine grain source. Okay, it is a fundamental to the Casagrande plasticity chart, which I will show in a while, okay, or later. Sorry, the Casagrande plasticity chart, which is currently the basis for the unified soil classification system, okay, or that's the USCS, okay, which will be our next topic. Okay, next meeting. Okay, don't worry, this is found in your book. Okay, so far we have defined the liquid limit, the plastic limit, as well as the plasticity index, which is the difference between the liquid limit and the plastic limit. Okay, so the liquid limit and the plastic limit, you derive this from the laboratory. Okay, so for the shrinkage limit, okay, now soil shrinks as moisture is gradually lost from it. No? So which means that, for example, if you put a soil under the heat of the sun, then it will gradually lose moisture, okay, lose moisture, and then the soil will shrink. Okay, of course, depending on the type of soil. No? Now, with continuing loss of moisture, a stage of equilibrium is reached, okay, at which more loss of moisture will result in no further volume change. Okay, so for example, in this figure here, you can probably have a soil material with an initial volume. Okay, this one here, V sub I, that's your initial volume, and then initially it has an initial water content, that's W sub I. Okay, and then as the moisture is gradually lost, okay, it can probably reach its liquid limit state. Okay, then as you continue losing moisture, it will go to its plastic limit state. Just continue losing moisture, then the soil might undergo its or might experience its shrinkage limit value. Okay, and then once it reaches the shrinkage limit value, then the soil will no longer shrink. Okay, so that's why here you now have a constant volume of soil. So here you have a decreasing volume of soil as the moisture decreases. But once the soil reaches its shrinkage limit state, then the soil will, uh, or the volume of the soil will already be stable. And that will now give you your final volume. Okay, so that means this one here, okay, V sub I minus a V sub F, or the initial volume minus the final volume, will now will give you the change in volume. Okay, and then from this initial water content, W sub I, until until the shrinkage limit, will give you the change in the moisture content. Okay? Okay, so referring back to this figure, so we can now define the formula for the shrinkage limit. Okay, so this shrinkage limit SL is now equal to uh, W sub I, okay, which is now in percent, which is defined as the initial moisture content when the soil is placed in the shrinkage limit dish. Okay? And then delta sub W is now the change in the moisture content that is between the initial moisture content and the moisture content at the shrinkage limit. So that's W sub I minus the change in the moisture content, this one here. So the initial water content, W sub I minus the change in the water content. Okay? So the initial water content is defined as the difference between M sub 1 and M sub 2, where M sub 1 is the mass of the wet soil path in the dish at the beginning of the test. Okay, and then M sub 2 is the mass of this time already dry, okay, of the dry soil path, okay, um, as seen in this figure here, okay. So in the shrinkage limit test, okay, this is now the soil path before drying, and then this is now your soil path after drying. So before drying, you now have an initial soil mass of M sub 1 and an initial volume V sub I. Then after drying, you now have the final soil mass, M sub 2, and the final soil volume, which is V sub F. Okay? So going back, you now have these terms here, okay, which is basically this one here, M sub 1 and M sub 2. Okay, so again, in the figure, you notice now that the soil is still sticking on the side of your dish, your porcelain dish, but after shrinking, then the soil path has now reduced in volume, moving away from the sides and also decreasing in height, soil height. Okay, so here we have an actual figure of the shrinkage limit dish. Okay, so here initially you have a wet soil. Okay, we're still sticking into the sides of the dish. And after drying, then this is now your soil material. No? So it's now moving away from the sides of the dish. And then this is top view. So if we look at it at the cross-section view, probably we can see that the height of the soil specimen has also decreased. Okay. So with this figure, okay, so um, from that figure, we can now define this change in water content, okay, or moisture content, Okay, so this one can now be, or this one now can be replaced by this one. And then this change in the moisture content before and after drying, okay, it's now given by the difference of the initial volume minus the final volume. That's big, I think this is piece of I, okay, multiplied by the density of water over M sub 2, which is now the mass of the dry soil after completely drying. Okay. So we can now substitute this formula here and then this formula here also. Then we can now get the shrinkage limit value. Okay. So another parameter that can be determined after we have uh, or in doing the shrinkage limit test is now what you call the shrinkage ratio, which is the ratio of the volume change of soil as a percentage of the dry volume to the corresponding change in the moisture content. Okay. So in formula, the shrinkage ratio, okay, is the ratio of the volume change. This is now the volume change as a percentage of the dry volume. That's the final volume to the corresponding change in moisture content. Okay. So delta V here is now defined as a change in volume, and delta M is the corresponding change in the mass of the mass of moisture. Okay. Then V sub F and M sub 2, we can just define by this one here, no? In the soil path after drying. Okay. So this one here, the change, the corresponding change in the mass, okay, can just be replaced by the change in volume multiplied by the density of water. Okay, so if you do that, then this can be canceled out. So what is left is now um, the final mass over the final volume after shrinking of the soil divided by the density of water. Okay? That's it should be defined as the shrinkage ratio. So if you now have an idea of the shrinkage ratio as well as the shrinkage limit, then you can also determine the specific gravity of the soil material. Okay. Um, I think earlier in our previous topics, we can determine the specific gravity of the material by some certain procedures. But another way of determining the specific gravity, okay, is by using this formula here, provided you have an idea of the shrinkage ratio, which is taken from here, as well as the shrinkage limit, which is, sorry, which is, yeah, defined by this formula. Okay. Okay, so that's another way of determining the specific gravity of your soil material. Okay, okay, so now if desired, okay, the maximum expected volumetric shrinkage as well as the linear shrinkage at the given moisture contents, W, can be calculated by this formula here, okay, where the volumetric shrinkage, that's Vs, in percent is equal to the shrinkage ratio, that's SR, multiplied by the given moisture content minus the shrinkage limit. Okay, we already know the formulas for this. Okay, and then the linear shrinkage then, okay, LS in percent is now defined by this formula here, okay, where Vs is defined as the volumetric shrinkage. Okay, so this one here. Okay. Now, typical values of a shrinkage limit for some clays are given here. No? Okay. So I think um, for Montmorillonite, you have this range of 8.5 to 15, huh? The shrinkage limit, then the elite, this range here, and then the highest shrinkage limit is the kaolinite, around 25 to 29. Okay? But of course, for your specific soil, you can always try to do a shrinkage limit test in the laboratory. Okay. Um, Now, the relative consistency, the relative consistency of a cohesive soil. Okay. So when we say consistency, these are the moisture levels, no? The moisture levels in your cohesive soil. So the relative consistency of a cohesive soil, okay, in the natural state can be defined by a ratio called the liquidity index. That's Li, wherein Li is defined as the moisture content, the in situ. Okay, that's the on-site moisture content. That's not the moisture content that you determine in the lab, but the in situ. Okay, when you say in situ, that's the one in the field. No? That's the in situ moisture content of the soil minus the plastic limit over the difference between the liquid limit minus the plastic limit. Okay? So with these definitions, okay, with this definition, the in situ moisture content for a sensitive clay may be greater than the liquid limit. Okay? In the case of a sensitive clay, so if the in situ moisture content is greater than the liquid limit, then it would follow, since you have the same plastic limit here, it would follow that the liquidity index would be greater than 1. Okay? Now, these soils, when remolded, can be transformed into a viscous form to flow like a liquid. Okay. Now, soil deposits that are heavily overconsolidated may have a natural moisture content less than the plastic limit. Okay. Now, so in this case, if the natural moisture content is less than the plastic limit, so that means this one is larger than this one, then the liquidity index will be negative, or less than 0. Okay. Now, again, in practice, for example, the liquidity index is useful when we would like to determine the active zone depth, okay, the active zone depth for our expansive soil material. Okay. For example, in the geotechnical report, when we say that, okay, for that site, um, you have an expansive soil material, okay, by properties, okay, by property, you have an expansive soil material, but you have to check the location of that material in the field if it is within the active zone. When you say the active zone, this is the zone where there is a change in the moisture content. Okay. Um, for example, during heavy rainfalls and during the dry seasons. No? For example, when you encounter El Nino or La Nina, then you now have evaporation and infiltration happening within the ground. No? Okay, I think you learned this in hydrology. Okay, so there will be a change in the moisture content. Okay, now, so if you try to plot the liquidity index for a number of days, no, or in the seasons within a year, if you try to plot that, okay, with respect to them for a particular site, okay. Now, if there are changes, then you would know, or if there are changes in the liquidity index, you would know that there is change of moisture happening, okay, which can now be treated as the active zone, okay. So that means that beyond the active zone, there is not much change in the moisture content in the ground, no? Depending on the depth of the groundwater level. Okay, so again, these groundwater levels, you will be discussing this in hydrology. Okay, so in geotechnical investigation, it is very important that we have accurate measurements of the groundwater level. Okay, in our case, we normally use a very quite we use automatic drilling rigs, which is a bit accurate, and then we also use automatic water level recorders, no? Which we try to drop into the borehole, and then we try to measure the groundwater levels for that particular site. Okay, yeah. Because again, the problematic soils, such as the collapsible soils, the expansive soils, and the liquefiable soils, they are a function of the groundwater level. Okay, so depending on where the soil is located, above or below the groundwater level, normally we have collapsible soils and expansive soils above the groundwater level, while we have problematic soils such as liquefiable soils and or compressible soils below the groundwater level. Okay, so that's why during geotechnical investigations, I am very strict in the measurement of the groundwater level in the field. Okay, normally I ask our drillers to measure the groundwater level from the start of the drilling works until we finish the drilling works. They always measure the groundwater level if there are changes with time. Okay. Um, lately we were doing, I just recall that lately we were doing a um, drilling work somewhere in Luzon. And but this is just about the borehole is about 15 meters, about 10 to 15 meters away from an inactive fault line. Okay, we were investigating the borehole. Within an inactive fault line. Then, while we were measuring the groundwater levels every day, we found out that the groundwater level is decreasing. Okay, it's not stable. So yeah, maybe the water is going somewhere else. Okay, due to the location of that inactive fault line. Yeah? Okay, so when we say fault line, there are two types of fault lines. You have the active fault line and the inactive fault line. So I guess you will be discussing this in your geology subject. Okay? Now, in geotechnical reports, normally we try to assess liquefaction, for example, according or based from the active fault lines within the Philippines. Okay, this is established in PIVOX. Okay, but in some of our project sites, such as the geothermal sites all over the Philippines, these sites are basically comprised of inactive fault lines, which means that they have not been active for the last 10,000 years, for example. It's beyond our lifetime, actually. Um, but they are there emitting steam. Yeah? Okay. So if some of you here are from Leyte or from Sorsogon or from Kidapawan or from Negros, okay, if you see those steams coming out from the mountains, okay, these are actually um, the geothermal steams, okay, which I have been visiting for the last 3 years, no, when I first worked in the industry. Okay, so I've been visiting all these sites no, for 3 years. Yeah. So I move a lot no, all over the Philippines. Okay, okay. So so that's the liquidity index. No? Okay, so this is a very useful parameter in assessing expansive soils, no? Which we always put in our report. Okay. Now, another index that is commonly used for engineering purposes is the consistency index, no, or CI, okay, which may be defined as the liquid limit minus the in situ moisture content over the liquid limit minus the plasticity index. Okay? So in this formula, if the in situ moisture content is equal to the liquid limit, then the consistency index can be treated. It will be equal to zero, no? Because yeah, the numerator will be zero. Okay? And then if the in-situ moisture content is equal to the plasticity index, okay, then this consistency index will be equal to 1. Okay, so this is just how we interpret the consistency index. Okay, okay. Now, because of the plasticity of the soil, okay, which is caused by the adsorbed water. Okay, so again, we in our previous discussions we were discussing about this adsorbed water in the clay material. Okay, so the because of this adsorbed water that surrounds the clay particles, we can expect that the type of clay minerals and their proportional amounts in the soil will affect the liquid and the plastic limits. Okay. Yeah. Uh, Now, Skempton in 1953 observed that the plasticity index of a soil increases linearly with the percentage of clay size fraction. That's when you say clay size fraction, that's the percent finer than 2 micrometers by weight present, which is basically shown in this figure here. Okay, so if we look at this figure, we have here a plot of the percentage of the clay size fraction that's less than 2 micrometers, or two. We sometimes call this microns. Okay, 2 microns. Okay, less than 2 microns. And then here we plot the plasticity index. Okay, so here we have 4 plots for a Shellhaven clay, a London clay, a Weald clay, and a Horton clay. Okay, so if you notice the names here, these are foreign names because normally these we call them the temperate countries. Okay, countries with 4 seasons, such as London and Holland, for example, or these European countries. Normally, they are mainly composed of clay materials. Okay, so there they did some research and then they plotted the plasticity index of each of these materials. Okay, and then they tried to plot a line. Okay, so here you now have the 4 plots for different 4 clay materials, okay, derived from different countries. Okay. So the correlations of the PI, okay, so this one here, if you're seeing my cursor, the correlations of the PI with the clay size fractions for different clays plot separate lines. Okay, so if you notice the difference there, the difference in the lines, okay, um, this difference is due to diverse plasticity characteristics of the various types of the clay minerals present in those clays. No? So there might be some of those clays might have elite clay minerals or colinite clay minerals or montmorillonite clay minerals. Okay? So on the basis of these results, okay, this one here, the basis of these results, in 1953, Skempton defined a quantity called activity, which is the slope of the line correlating the PI and the percent finer than 2 microns. Okay. So then by formula, we now have the activity A is now equal to the plasticity index, where plasticity index is the liquid limit minus the plastic limit, if you try to recall, over the percent of clay size fraction by weight. Okay. Now, this activity parameter is used as an index for identifying the swelling potential of clay soils. Okay. So again, when we assess, okay, in the geotechnical reports, when we assess expansive soils, aside from the properties of the soil that will make it expansive, we also try to check the groundwater levels. Okay, we also try to check because a swelling clays, for example, will only happen above the groundwater level. Now, it will not happen below the groundwater level. Then we also try to check, even if it is above the groundwater level, we also try to check the active zone, okay, where you have changes, very high changes in the moisture content, which can be plotted using the liquidity index, this one here. And then we also check for the activity, okay, the activity of the soil um, sample. Okay, so we try to calculate for this activity. Okay, because again, these values here or these parameters here is part of our routine test. Okay, in all samples that we get from the from the site, we try to get these parameters as part of our routine tests. Okay, so now let's talk a little bit about the plasticity chart. Okay, which will be used later in the next in our next meeting. So Casagrande in 1932 studied the relationship of the plasticity index to the liquid limit of a wide variety of natural soils. Okay. Now, on the basis of these test results, Casagrande proposed, okay, a plasticity chart. Okay. Now, in this chart, the important feature is the empirical, we call it the empirical A line, that is given by this equation here, okay, pi equal to 0.73 times the liquid limit minus 20, okay, wherein the A line separates the inorganic clays from the inorganic silts, okay? So the inorganic clay values lie above the A line, and values for the inorganic silts lie below the A line. So if we look at the plasticity chart here, okay, so this is now your plasticity chart, okay, wherein the x-axis is the values of the liquid limit, and then the vertical axis are the plasticity index. So again, the PI or the plasticity index is the difference between the liquid limit LL and the plastic limit. That's LL minus PL. Okay. So this is now the A line. No? We call this the A line, wherein this A line is defined by this formula PI equal to this equation here. Okay. So again, above, okay, above the A line are the inorganic clays. Okay, this one here, the inorganic clays, we call them the inorganic clays. And then below the A line, we have the inorganic silts. Okay, so again, later on, we will discuss this in more detail when we go to the soil classifications. Okay, and then organic silts. Okay, so organic silts are plot in the same region. Okay, as the inorganic silts of medium compressibility. Okay, so if you look at this one here, this one, okay, if you look at these regions here, these are the regions for the inorganic silts of medium compressibility as well as the organic silts. Now, when you say organic, normally these are silts which have decayed plants and animals. No? Organic, which is organic. And then in this region, okay, the organic clays rather, the organic clays have the same region as the inorganic silts of high compressibility. Okay, yeah. So again, we don't like this term also, no? As far as construction is concerned, we don't like uh, highly compressible soils. Okay, so that's this one here. Okay, and then okay, so then aside from the A line, you also have the U line. Okay, so the U line is approximately the upper limit of the relationship of the plasticity index to the liquid limit for any currently known soil. wherein the U line is given by this formula here for the PI. Okay? So if we go to the graph to the chart again, this is now my A line, okay? And then this is now my U line, no? Which is now the boundary, okay, for my plasticity chart, which means that below the U line, okay, below the U line, we can consider them as cohesive soils. Above the A line can probably be the cohesionless soils, okay? Although there is some gray area there with respect to the silts, okay? And then further on, if we put here vertical lines that will divide these regions into 6 regions, then that will now be the regions for these different types of soil materials for different plasticities and compressibilities. No? For example, this one here is the organic clays of a low plasticity. This one here is the inorganic clays of medium plasticity. I hope you're seeing my cursor. And this one here are the inorganic clays of high plasticity, which we don't like as far as construction is concerned. And then this one here are the inorganic cells of low compressibility. Here, the inorganic cells of medium compressibility, as well as the organic cells. And then this one here are the inorganic cells of high compressibility, as well as the organic clays. Okay? So this one here is now what we call the plasticity chart, which will then be the basis later on in our next meeting for the classification of fine grain soils in the US classification system. Okay? As far as geotechnical engineering practice is concerned, we use the USCS system. Okay. So far, we have discussed the Atterberg limits. Okay. Now let's discuss a little bit about the soil structure. Okay. But before we continue, let me just look at my time. It's about 7:18 here in my watch. Maybe we can have a short break for 10 minutes. Okay. Maybe you want to have a toilet break. Okay, and let me just rest my voice a little bit. Okay, so please be back after 10 minutes. Okay, so maybe we can now continue with our lecture. Okay, so now let's try to discuss a little bit about soil structure. Okay, now soil structure is defined as the geometric arrangement of soil particles with respect to one another. Okay? Now, among the many factors that affect the structure are the shape, the size, and the mineralogical composition of the soil particles, and the nature and composition of the soil water. Okay? Now, in general, soils can be placed into two groups. Okay? You have the cohesionless soils and the cohesive soils. Okay. Now let's talk first about cohesionless soils. Okay. Now, the structures generally encountered in cohesionless soils can be divided. Now, we're talking of the soil structure here, can be divided into two major categories. Okay? You have the single grained and the honeycomb. Okay. Now, in the single grained structures, soil particles are in stable positions with each particle in contact with the surrounding ones. So the shape and the size distribution of the soil particles and their relative positions influence the denseness, no? Okay, that will influence the denseness of the packing. In this case, a wide range of void ratios is possible. That's why, for example, um, when we talk of relative density, okay, I think in the previous uh, meetings we have been discussing the relative density. There we can have a very loose condition, medium dense condition, and very dense condition. Okay, yeah. So this is because of the wide range of void ratios that is possible because of the arrangement of the soil structure. Okay. Normally in the field, we determine this relative density by using the drilling equipment based from the SPTN value, the standard penetration test value. We can determine. You can also determine this in the lab if you like. So to get an idea of the variation of the void ratios caused by the relative positions of the particles, then we can now consider the mode of packing of equal spheres. Ideally, although in reality we don't have equal spheres for soils, but for the moment, to understand the variation of the void ratios, why you're having different void ratios. So let's try to check the mode of packing of equal spheres. Okay. So what you're seeing here is a single grain structure. Okay, this one here. Okay, so again, you either have a single grain or a honeycomb structure in the case of a cohesionless soils. Okay, so this one here is a single grain structure, wherein A is in a loose state. In a loose state, single grain structure. Then here you have a dense state, okay, of a single grain structure. Okay, so in the loose state, okay, you have a higher voids, and then in the dense state, you have smaller voids. Okay. So again, to have some idea on the variations in the void ratios, again, if you recall, the void ratio is defined as the volume of voids over the volume of solids. Okay? So that means the higher the void ratio, the higher is the spaces within the soil particles. Okay? The smaller the void ratio, that means the smaller are the spaces um, within the soil particles. Okay? So again, to understand these different values in the void ratios, we can try to consider the mode of packing of equal spheres. In this case, for example, take note, this is in plan view. So you can imagine you have spheres, you put in the table, then you're looking above it. Okay. So, so in a very loose packing, okay, this one is A. You can imagine that, just try to imagine that here you have two layers of equal spheres. Okay, so the one you're seeing here is the first layer, and then there is another layer of soil on top of each particle. Okay, but exactly on the same location. So if that is the arrangement, then you have a very loose packing. Okay, yeah. So that in that case, you have a void ratio equal to 0.91. Okay. Now in here, okay, again, you try to imagine that you have two layers, but this is now the first layer, the one with the gray color, and then these broken lines here is now your second layer. So again, you're looking at the top. Okay, you're looking at the top. So in this case, you have minimized the voids, or the spaces between the particles, okay, because you have place the sphere in between. For example, these are four spheres, the gray ones, then you have a sphere at the center. Okay? So in that case, you have a very dense packing, and that probably gives you a void ratio of 0.35. Okay? So for example, this one here, this 0.91 value, okay, let's try to derive that. Okay. So for example, in the case of a very loose state of packing, okay, if we isolate a cube with each side measuring d, okay, this one here, we isolate a cube with each side with d, with the dimension d. Okay. So which is equal to the diameter of the sphere. Okay, then with that one, the void ratio can be calculated as this one here, which is now the volume of voids over the volume of solids. Okay, if you try to recall, but the volume of voids is equal to the total volume. In this case, the volume of the cube, okay, which is now d cube. Okay, because you have a cube with a dimension d, that's d cube, okay, minus the volume of the sphere, okay, or the solid, okay, or the sphere in this case, inside the cube. Okay, so you have here, you have the volume of the cube, that's d cube, okay, and then this is now the volume of the sphere within the cube. Okay, so then this is now the volume of the cube, that's d cube. Then this is now the volume of the sphere, that's pi d cube over 6, okay, which will now give you this one. If you substitute these values here, this is now d cubed, and then Vs is equal to this one over Vs. This is now your Vs. Okay, and then from here, you can just factor out d cubed. Then you can calculate the value. That gives you a void ratio of 0.91. Okay, so that's why here you have a value of 0.91 for a very loose packing. Yeah? So this one representing this condition here. Yeah? So this packing here is now what you call a cubical or a simple cubical packing. Yeah? This one. This is now called a cubical or a simple cubical packing. Okay, so for the very dense state of packing, okay, um, then we can isolate here a cube, okay, going back here, okay. So we isolate a cube, okay, this one here, no, we try to cut a cube, okay. So in such a way that that cube, okay, is comprised of this half of this, each of this sphere. Then you have one sphere here, okay, yeah. So then here the the hypotenuse is 2d, okay, and then the dimension on the size is d over square root of 2, as per the Pythagorean theorem, for example. Okay. Um, okay. So with that, okay, then just try to substitute that this the same approach here. Okay. Then the void ratio, the value of the void ratio based on this formula will now be equal to 0.35. Okay, so that's why here you have a value of 0.35 for the very dense packing, for example. Okay, so this packing here is now what we call a pyramidal packing. Okay. Um, Okay, so aside from those two packings, there are other types of packing of ecospheres. Okay, between the loosest and the densest states. Okay, um, for example, the simple stagger packing as well as the double stagger packing. Wherein the simple stagger packing in this pattern, each sphere touches six neighboring spheres in its own layer. Okay, and then the spheres in different layers are stacked directly on top of each other. Okay, so if you look at the figure, that's this one here. Okay, that's a simple um, stagger. No, okay, so that means each sphere is touching six other spheres on each on its layer. Okay, and then on the upper layer, they are being stacked directly on top of each other. Okay, so kumbaga patong-patong lang gyapon rin. So that means in the plan view, this one is the same as this one, no? For each layer. Okay, so that means here you cannot see the second layer because it's just on top of each other. Okay, so in this case, in this packing, the void ratio is equal to 0.65. Okay. Now, in the double stagger packing, this is similar to the single stagger pattern, except that each sphere in one layer has slid over and down to contact two spheres in the second layer. Okay, so something like this. Okay, yeah. So this the gray sphere here is the first layer, and then the broken line sphere here is your second layer. Okay, so yeah. So in this case, in this configuration, then the void ratio is equal to 0.43. Okay, so that means if we go back here, now this one here in this arrangement, so the void ratio is 0.35. In this arrangement, the void ratio is 0.43. Sorry, yeah, 0.43 is one here. Okay, and then in this arrangement, the void ratio is um, sorry, this one here is, what is that? Yeah, this is 0.65 rather, no? This one is 0.65, okay? This one is 0.65, okay? And then this one is 0.43, the void ratio, and then this one is 0.90, sorry, 0.35 and then 0.91, okay? So 0.91, 0.65, okay? 0.35, then 0.43, no, for the void ratios. Okay, so that gives you the idea of the possible arrangement of the particles for different types of void ratios. No? Okay, so again, the void ratio is defined as the volume of voids to the volume of solids. Okay. Now, real soil differs from the equal spheres model in that soil particles, um, which are neither equal in size nor spherical. No? This, we are now talking of the real soils. Okay? Now, for the real soils, the smaller size particles may occupy the void spaces between the larger particles. Okay, for example, in the case of a well-graded sand material, which we'll discuss later, the USCS system. Okay. Now, thus the void ratio of soils in this arrangement is decreased compared with that for equal spheres. However, the irregularity in the particle shapes as well, no? Okay, generally yields an increase in the void ratio of your soils. Now, as a result of these two factors, the void ratios encountered in real soils have approximately the same range as those obtained in equal spheres. Okay, because of these conditions. Okay? Now, aside from the single grain structure, this one. We also have the honeycomb soil structure. Okay. Now, in the honeycomb structure, relatively fine sand and silt form small arches with chains of particles. Okay. Yeah. So, for example, this one here, sorry, this one here. Okay. So this is an example of a honeycomb structure wherein these are now your soil solids. Okay. And these are now the voids. So they form something like this. Okay. This is a honeycomb structure. Now, soils that exhibit a honeycomb structure have large void ratios, okay, and they can carry an ordinary static load. However, under a heavy load or when subjected to shock loading, the structure would break down. Huh? It would break down, which results in a large amount of settlement. Okay. In practice, we only have a certain degree of limitation with our settlements. Okay. Yeah. Okay. So for cohesionless soils, we have again two types of soil structures. You have the single grain structure and the honeycomb structure. Okay. So now let's go to the cohesive soils. Okay. So earlier we just discussed the cohesionless soils. Okay, now we have the cohesive source. Now, the reason we try to differentiate between cohesionless source and cohesive source, because later on, when we go to the strength of materials, the shear strength of the soil materials, the shear strength would depend if we are talking about cohesionless soils or cohesive source. Okay. So in the geotechnical report, we try to separate or we try to segregate the shear strength parameters for cohesionless soils and cohesive soils. No, with respect to the cohesion parameter as well as the friction angle parameter, no, for your shear strength um, parameters of the soil. That will be our later. That will be our topic later on. Okay. Now, in the case of cohesive soils, to understand the basic structure, one needs to know the types of forces. Okay. So in cohesive soils, we talk of forces. Okay. So these are the types of forces that act between the clay particles suspended in water, considering the negative charge on the surface of the clay particles, okay, as well as the diffuse double layer surrounding each particle. So if you recall, I think during our first meeting, we have discussed this diffuse double layer in the case of a clay particle. Now, when two clay particles in suspension come close to each other, then the tendency for the interpenetration of the diffuse double layers results in a repulsion between the particles. Okay. At the same time, an attractive force exists between the clay particles that is caused by the so-called van der Waals forces. If you still recall your physics, okay, these van der Waals forces, and is independent of the characteristics of the water. Okay. Now, both repulsive and attractive forces increase with decreasing distance between the particles, but at different rates. Okay? Now, when the spacing between the particles is very small, then the force of attraction is greater than the force of repulsion. Okay? Now, these are now the forces that are treated by the so-called colloidal theories, right? Because sometimes in soils, we try to consider its behavior in terms of its colloidal nature. Okay. Now, considering the behavior of clay. this time in the form of a dilute suspension. So when the clay is initially dispersed in water, the particles would repel one another. And so this repulsion occurs because with larger interparticle spacing, this time the force of repulsion between the particles will now be greater than the force of attraction. Again, so-called van der Waals forces. Okay. Now, the force of gravity on each particle is considered to be negligible. Okay. Thus, the individual particles, okay, may settle very slowly or remain in suspension, undergoing what we call a Brownian motion, okay, which is a random zigzag motion of colloidal particles in a suspension. For example, when you do the hydrometer test, no, for example, okay, the fine particles there might undergo Brownian motion, no, when you try to let it settle, okay, especially the clay particles. So the sediment formed by the settling of the individual particles has a what you call a dispersed structure. Okay, and all particles are oriented more or less parallel to one another. No? So something like this. No? Okay, so this is now a dispersion structure. Okay, now if the clay particles initially dispersed in water would come close to one another during a random motion in suspension, then they might aggregate. They might aggregate into what we call as visible flocks with edge-to-edge contact. In this instance, the particles are held together by electrostatic attraction of positively charged edges to negatively charged faces. Okay. Now, this aggregation is now what we call flocculation. Now, when the flocks become large, they settle under the force of gravity. Okay? Now, in this case, the sediment formed in this manner has a flocculent structure. Okay. So if you look at the figure, this one here is what you call a flocculent structure or a non-salt flocculent structure. That means, for example, if it is dispersed in fresh water, for example. Now, when salt is added to a clay water suspension, such as seawater, for example, that has been initially dispersed, then the ions in the particles tend to depress the double layer around the particles. Okay? Now, this depression reduces the interparticle repulsion. Okay? Now, the clay particles are attracted to one another to form flocks, and then they would settle. So in this case, again, a flocculent structure of the sediments are then formed, which is something like this. Okay, so this is now a sediment structure in the case of a salt flocculated structure. Okay, so something like this. So these are like sheets, the clay sheets. If you try to recall, okay, the clay minerals. Okay, so clays that have flocculent structures are lightweight, okay, and possess a high void ratios. Okay, so clay deposits formed in the sea are highly flocculent. Okay, most of the sediment deposits are formed from fresh water would possess an intermediate structure between dispersed structure and a flocculent structure, giving lower void ratios. Okay. Now, a deposit of pure clay minerals is actually rare in nature. Okay. Sometimes it's a mixture of silts and clays and so on and so forth. Silty clay, clay silts. Okay. And a combination of clay minerals. Okay. Um, Now, when a soil has 50%, okay, so when a soil has 50% or more particles with sizes of 0.002 millimeters, or that's a 2 microns or less, okay, it is now generally termed as clay. Okay, so normally when we say cohesive soils, automatically we always think of clay soils. So again, we will have the formal definition of this one next meeting. Okay, or in the next meetings. Yeah? Okay. Um, Studies with scanning electron microscopes have shown that individual clay particles tend to be aggregated or flocculated in sub-microscopic units. Now, these units are referred to as domains. Okay. Now, the domains then group together, and these groups are called clusters. Okay. Now, clusters can be seen under a light microscope. Okay. So, this grouping to form clusters is caused primarily by the interparticle forces. Okay. So, the clusters in turn would group to form PEDs. Okay. So, to have an illustration of that, okay. So, we have here a soil structure for cohesive soils. Okay. Sorry, in this case, for a silt size rather, silt size particles. Okay, so here you have the arrangement of the PEDs. Okay, we have the PEDs. Between that is or the macropores. Okay, the voids between it. Okay, and then here, okay, yeah, again you have the silt size particles. You have here the domains. Okay, um, and as well as the clusters. Okay, this one here. So these are domains, these are the clusters. Okay, so yeah, so we have the domains would group together to form clusters, and then clusters okay, would group together to form PEDs. Okay, so you have here the domains, the PEDs, okay, sorry, the domains, the clusters, and the PEDs. Okay, so this is the soil structure in the case of a silt-sized particles. Okay, so just some remarks in the case of clay soils. Okay, so again, in terms of structure, you have here the dispersed structure, which are formed by settlement of individual clay particles, more or less in a parallel orientation. Okay, so again, that's this one here. Okay, the case of clays. Then for flocculent structures, these are formed by the settlement of flocks of the clay particles. Okay, and then you have the domains, which are aggregated or flocculated submicroscopic units of the clay particles. Then you have the clusters, which are the domain group to form clusters, which can be seen under a light microscope. Okay, and then clusters group to form PEDs, which can be seen even without a microscope. Okay. Okay. So yeah, I guess that's it. Okay. Now, before I go to the some problems, do you have any questions or clarifications so far? Okay. I guess if there are none, let me proceed with uh, the problems. Okay. So here we have an example wherein you have here the results of sorry, there's a chat here. I think there's a question. Okay, sorry. Yeah, so there's none. Okay. Um, so here you have an example of results of a shrinkage limit test. I'm not sure if you will do this in the lab. Okay. So in the shrinkage limit test, you have here the initial volume of soil in a saturated state. Okay. Then with this value here, then you have the final volume of soil in a dry state, which is given here. And then the initial mass in a saturated state given by this value. And then you have the final mass in a dry state given by this value. Okay. So then we are asked to determine the shrinkage limit of the soil. Okay. So from the previously defined equations, we have here the formula for the shrinkage limit rather, shrinkage limit, which is now the initial mass minus the final mass over the initial mass. Okay. So we're in, this is now the initial mass, and then this is now the final mass. This is in the saturated state, this is in the dry state. Then minus this one here, which is now the initial volume, minus the final volume over m sub 2, okay, which is this one here, multiplied by the density of water, okay? And then we just multiply both by 100 to just convert it to percentage, wherein the density of water is equal to 1 gram per cubic centimeter, since here the units are grams and cubic centimeters. Okay. So just try to substitute these values, okay, here in these formulas, okay, then we can get now the value for the shrinkage limit, which is now 17.28%. Okay. Okay. Um, so, considering the same data, we are also asked to determine the shrinkage ratio of the soils, okay, and also estimate the specific gravity of the soil solids. Okay. So if we try to recall, this is the formula for the shrinkage ratio, which is now the final mass over the final volume multiplied by the density of water. So we just substitute here the values, then we get a value of 1.89. Okay. So, okay. So I think the units will cancel out. So that's grams and grams, cubic centimeters and cubic centimeters, centimeters. So that means this shrinkage ratio is unitless. Okay. Okay. Then for the specific gravity, okay, so if you try to recall, this is the formula, okay, the formula. So that's 1 over the shrinkage ratio minus the shrinkage limit over 100. Okay? So we just substitute the value here for the shrinkage ratio and substitute the value here for the shrinkage limit, okay, this one. Then we can get an approximate value of 2.81. Okay. So in this case, you have a larger specific gravity. Okay. Normally, we have around 2.65. Okay. So again, referring to the same example here, the same given. Okay. If the soil is at a moisture content of 28%, okay, Then we are also asked to estimate the maximum volumetric shrinkage as well as the linear shrinkage. So for the volumetric shrinkage, okay, so again by formula, that's equal to the shrinkage ratio minus the moisture content, times the moisture content minus the shrinkage limit. Okay. So here, this is given, that's 28 for the moisture content. We have already solved this for the shrinkage limit, and then this one is the shrinkage ratio. So with that, we have the um, volumetric shrinkage equal to 20.26%, for example. So that means from the initial mass and initial volume to the final mass and the final volume, then the volumetric, sorry, the volumetric shrinkage, assuming a moisture content of 28%, is about 20%. Okay, this is about 20%, around 20% uh, from the initial volume. Okay. Now, for the linear shrinkage in percent, okay, so again, this is the formula for that. Okay, then I think the parameter is only the volumetric shrinkage. So if we substitute here the value for the volumetric shrinkage, then we have a linear shrinkage of about 6%. Okay, 6% from the initial value. Okay. Uh, okay. Yeah, I guess that's the end of my lecture for today. Um, so I think we just demonstrated the formulas which we have presented so far. So do you have any questions or clarifications so far? So again, in practice, we normally specify the routine test. So for the routine test, we normally specify or we normally require the moisture content for each sample. I mean, I'm talking about for each sample. Normally, we extract samples every 1 or 1.5 meters from ground surface using our drilling equipment. Okay, so for each sample, we try to require the moisture content. Okay, the Alterberg limits. Okay, um, or the consistency. Okay, and then we also require the grain size test. Okay, to check for the grain size distribution curves. Okay, yeah, as well as okay the unit weights. Okay, um, and yeah, we also require to have the USCS classification. Okay, um, to be placed in the lab test results. Okay, because I just recalled one of you was asking this question last time. So that means if normally, for example, normally in practice, we try to drill about 30 meters. Okay, 30 meters. Because 30 meters, as per the NSCP code, um, it is here wherein we try to determine the soil profiles, okay, needed for seismic assessments. Okay, seismic assessment. Okay, we also put that in the geotechnical report. Okay, Okay, so that means that if you have 30 meters depth, for example, if let's say, for example, I specify to have it tested in the lab every 1.5 meters of soil sample extraction. So that means in a 30-meter depth of geotechnical drilling work, then you will expect 20 soil samples in one borehole. No? We call it a borehole. Okay. That's a 20. That means you will need to test for grain size, Atterberg limits, and moisture contents, as well as the unit weights, each of these 20 samples. Okay. Yep. So that's the number of tests. Then, for example, in one site, we have about 10 boreholes at about 30-meter depths. So that means that's about 10 boreholes times 20 samples per borehole. So that means for that project, you have to do all these tests 200 times. Okay. Yeah. So we bring the samples to the lab. So that's why it's important to know these basic tests. Okay. And after that, we get the samples from the lab, and then we start with our assessments. No? We start with our geotechnical assessments. So without these results, we cannot do anything in the geotechnical report. Okay. So that's why it's very important that we do these tests. No, these tests that we have discussed in our first three meetings. These are basically the routine tests that we do. So every day in my work, I always look at these lab test results. Okay. Any questions so far? So again, in practice, we use the first 30-meter depths for the seismic profile, soil profile, for seismic assessments. Okay. But in terms of liquefaction assessment, okay, we only consider as per the DPWH and the ASH to codes. Um, we only assess until 20-meter depths. Okay, 20-meter depths. So then in that 20-meter depths, we need to know if the soils have the properties for a liquefiable soil material. So we do an initial screening. Okay. Yeah. So for example, the one I attended earlier, the liquefiable depths that we have identified is about 18-meter depth. Okay? 18-meter depth. Okay. So do you have any questions or clarification so far? It may not be on the lecture, or maybe you have some practical questions that you have heard of outside, okay, and you need some clarifications. So I think my colleagues will just give you further examples, for example, for seat work. Although I understand that this Thursday will be your first exam, okay, because it was postponed last Thursday. Okay, so good luck with your exam. Okay, so I hope you had 1 week to study for your pre-midterm exam. Okay, are there any questions or clarifications so far? Or do you have any concerns? Okay, let me just stop share.